My name is Serena Ferraro and I'm an aerospace and astronautical engineer from Vacaville, California. I attended the University of Naples, graduating summa cum laude in 2011 with a master's degree in aerospace and astronautical engineering. I traveled all over the world, from Italy to most of the European countries, to Africa to United States. Now I'd like to tell you about one of my favorite projects I've been involved with. In collaboration with Mermet Group and the Department of Aerospace Engineering of Naples, I developed a piezoelectric energy harvesting system from vibrations for wireless sensors. The device, integrating piezoelectric materials, is able to convert vibrational energy into electrical one. It has been applied in a train derailment detector system to supply the wireless transmission unit, which sends warning messages to the driver. We started with the basic analytical model, which assumes as configuration a cantilever beam with a mass placed on the end part. On each side of the beam is glued a piezoelectric element. The two elements form then a bimorph since they're wired in parallel. We then developed a new model useful to understand which is the most efficient way to wire the piezoelectric elements, and it turned out to be the parallel connection. We also provided a new expression for the optimal resistive load. We created a numerical model in Patron and performed a model analysis on it. Completed the analytical phase, we proceeded to the realization of the prototype and the various design choices done in order to optimize the performance. We chose the piezoelectric element B876A11 Duract. We used the cantilever beam because it results in the lowest stiffness for a given site and the highest average strain for a given force input. The layer is made of spring steel because of its high yield strength, which gives an excellent fatigue behavior. A cam configuration was adopted in order to reduce the mechanical phase shift between the beams and because of its compact shape that optimizes the space requirement. The signal used for the tests is generated by a random signal generator DuckPad 6052E National Instruments. It was possible developing a program in LabVIEW. The signal passes through an amplifier and is input to the shaker on which is mounted the prototype. The voltage generated across the piezoelectric elements is then recorded with the data recorder LMS Cadas Mobile or with an oscilloscope if it's higher than 10 volt. To perform realistic tests, we measured the signal on the freight train. From the spectrogram, it is possible to note that the highest levels of acceleration are included in the interval 40-50 Hz. From the acquisitions done, 2 time segments were chosen to be used as input signals for the tests and are shown in the graphs. Testing the prototype, we obtained the optimal configuration which maximizes the power generated. Was then tackled the problem of the converse piezoelectric effect and found a solution by wiring a tight bridge to each piezoelectric element. Since the power required for the specific application is about 20 mW, some tests were carried out wiring more bimorph in parallel in order to increase the energy produced. This is a video that shows a LED connected to the prototype which turns on with the energy developed. The intermittent light is due to the absence of a capacitor in the circuit. Thanks for your attention. I'm extremely excited about hearing back from you and about the potential of working for Tesla Motors.